Welcome to refraction at a plane surface. A plane surface is a flat surface. The term plane is a mathematical concept, and it essentially is a two-dimensional flat shape that extends to infinity in all directions. In this topic, we're going to be using the term plane to describe the interface between two materials. The changeover from being inside one material to being in another happens at the interface between those materials. In this simulation, I have a laser, and at the moment the laser is starting off in air and then moves into the second material, which at the moment is also air. These two materials have a property of light passing through them called the index of refraction. So all materials that allow light to pass through them that are transparent will have an index of refraction, and that describes the speed of light in that material. We know that the speed of light is 3 × 10⁸ meters per second, but that's in the vacuum of space. Whenever light travels through another material, it will have an index of refraction. It will be slightly slower than 3 × 10⁸. And the greater the index of refraction, the slower the light travels. So at the moment we have a laser and it is moving in a straight line. I'm going to show you that with my protractor. Okay, so I'm setting up the protractor so that the 0 is in line with this dotted line here, which is the normal, and this is an imaginary line at 90 degrees to the interface. And we describe refraction by comparing the angle of incidence, which is this angle here between the normal and the light ray. We compare the angle of incidence to the angle of refraction, which is the second angle down here between the normal and the light ray. If I change the index of refraction for the second material and I gradually make that bigger, then what we will observe is that the angle of refraction decreases. The light bends towards the normal. And the higher that second index of refraction, the more it bends. We also see that some of the light has been reflected, and that's because the dramatic change between the first material and the second is a little difficult to overcome, and some of the energy at that interface doesn't quite make it into the material and it's reflected instead. If I change the index of refraction of the first material, then we get a slightly different type of behaviour happening. We can see that the light ray is bending away from the normal. Let me show you that with the protractor. So at the moment, the angle of refraction is 30 degrees. If I increase the first material's index of refraction to something like water or maybe glass, then you can see that that angle is actually increased. It's bent away from the normal. And this is the pattern that we observe. If I leave these settings like this and I start adjusting the angle of incidence, then I get another effect happening. So the more direct the laser is, the easier it is for the light to make it into the other material. We start to get some reflected light here, and as I increase that angle, it gets harder and harder for the light to make it across that boundary, and then at some point we get the angle of refraction being 90 degrees. So as it approaches the interface and becomes 90 degrees, all of the light is then internally reflected. So let's do that with the protractor. So what we're interested in is the angle of refraction, which is this angle down here. When that angle gets to 90 degrees, it cannot get any further. And what you have instead is all of the energy being totally internally reflected. So as that gets closer and closer to 90 degrees in the simulation, That's about as close as I can get. And then we have total internal reflection. This happens when the angle of refraction is 90 degrees. And the angle at which this happens is different for different indexes of refraction. So for glass, the angle of incidence to get total internal reflection is about 43 degrees. If we change to water, and we do that experiment again, and we drag the laser across and we watch the angle of refraction getting larger and larger, closer and closer to 90 degrees, it happens approximately there, which is about 49 degrees. So it depends on the index of refraction, and we're going to have a look at the mathematics of that in a little bit. If we have an interface between two materials and a light ray travelling from one into the other, then the direction in which it bends will depend upon the relationship between the indexes of refraction. So for example, if we have air and we have glass, then we say that the index of refraction for N1 and N2, we compare them like this. So N1 is smaller than N2. Okay. N1 for air is about 1.0 and glass about 1.5. And when you have an increase in the index of refraction, then you are going to have the light bending towards the normal. Okay, here's the normal at 90 degrees, and the light ray is bending towards the normal. If you have the opposite situation, there's our interface, here's our light ray. Let's imagine that we have water going into air, and this is N1 because it's where the light ray starts, and N2 it's the second material that it goes into. Well, in this situation, N1 is actually larger than N2, and in this situation the light ray is going to move away from the normal. Okay, and it's all to do with the speed that it's travelling at. I want to use the analogy of cars. So if we have a car, this is viewed from above, and these are the four wheels on their axles moving in the same direction as the light ray, then what's happening to that car is that this front wheel here is entering the glass first. Now in the glass, the speed of light is slower. So this one wheel here is going to suddenly slow down as soon as it enters this new material. And because that wheel slows down, it turns the rest of the car toward it. This happens when you're driving along and one side of your vehicle goes through a puddle, a big pool of water at the side of the road. Your vehicle will try to turn towards that puddle. And that's because the wheels on that side have slowed down. Same analogy works for speeding up. So there's our car, and here's that car entering the new material, and the first wheel to enter that new material again is this one here, except in this example we've gone from water into air, and light travels faster in air, so this wheel is suddenly going to speed up, and as it suddenly speeds up it rotates the car the other way. And that is essentially what's happening to these rays of light, because remember, these rays of light are made of wavefronts, and if I sketch the wavefronts, then it looks very similar to the analogy with the cars. Okay, so here are my wavefronts moving along, and what happens here is this part of the wavefront is suddenly going to slow down. It's not going to have progressed as far as the other side, so it turns. Same with this one over here. The wavefront would be continuing like this if it was going at the same speed, but it hasn't. It's suddenly sped up. So that part of the wavefront is actually ahead of where it should have been, and it's turned. It may be easier to think about it in terms of the cars than the wavefronts, whichever works for you. It's important that you understand the mathematical relationship between the index of refraction, the speed of the light, and the angles of incidence and refraction. So we'll start off with the index of refraction. So to calculate any one of these values, we need to know the speed of light and the velocity of light in that material. In your course, this is written like this. You can think of the S as being the speed of light in that substance, in that material. So we know, for example, that the index of refraction of glass is 1.5, and that means we should be able to use that information to calculate the speed of light in glass. So let's have a go at that quickly. So the speed of light in that material is the speed of light in a vacuum divided by 1.5, which is 3 times 10 to the 8 divided by 1.5, which gives us 2 times 10 to the 8 meters per second. So it's quite a dramatic reduction in speed from the one that we are used to. And things like water reduces the speed of light. Diamond, for example, has an index of refraction of 2.42, which is very dramatic indeed, and it causes all sorts of splitting of the white light into different colours, and that's why diamonds have the optical properties that they do. It's all because of their index of refraction. The other equation that you need to be able to use is the relationship between the index of refraction of the first material, the second material, and the angles. So the index, the incident angle is there, index of refraction of the second material, and then the angle of refraction. Okay, so we've got the properties of the first material and the properties of the second material. You may see this written in a slightly different way. In some other textbooks. This is the way it's presented on your course, and I find this one the easiest to remember because all of the ones are on the same side as the ones, and the twos are on the same side as the twos, whereas this one there's a crossover effect, and it's easy to get this one wrong if you're trying to do it from memory. When we're studying total internal reflection, what we have is we have an incident ray, and the refracted ray is here. It's moving along that interface. And what we have is we have an angle of incidence, and the angle of refraction is 90 degrees. And just for a moment, you have the light ray moving along the interface, and if you move this angle ever so slightly, even by, say a millionth of a degree further down, and make that slightly larger, this ray disappears and you get a reflected ray, and that follows the rules of reflection in the same way that you've previously studied. So the important thing to note is that the angle of refraction is 90 degrees. So if we have a look at our equation, then what we have is we have this value here is 90 degrees, and sine 90 is equal to 1. So this term disappears when we're talking about total internal reflection. This needs to be true in order to do this algebraic, to make this algebraic assumption. So what we have in the end is that the incidence angle, known as the critical angle, because it's the angle at which total internal reflection happens. The critical angle is a threshold angle. Above this, you are going to get total internal reflection. So what we tend to do is we tend to think of it as being, instead of theta subscript 1 for the incidence angle, we tend to write it as theta subscript c for critical angle. And we rearrange the equation. We get that. So you can always work out what the sine of the critical angle is by doing the ratio of the second to the first material's index of refraction. Notice that that is a threshold value, so you can have an incidence angle that's larger, but you're not going to get any refraction. It's all going to be totally internally reflected. So this is a threshold above which you have total internal reflection. A very important application of total internal reflection is in fibre optics. And fibre optics is a way to send light signals over very, very long distances. It's done using a cable with material on the outside to protect the central core, which is made of glass or plastic. So that is the core. And then on the outside, you have the cladding. And the cladding is a material that's going to help create that total internal reflection. So here is a cross section. There's the cladding, here's the core, and there's the lower layer of cladding. And the idea is that the light travels through this glass core and continues its journey. But if the wire gets bent, then what's going to happen is that the light is going to come in contact with the edge of that glass core, and it needs to be redirected towards the center. So we have a refractive index of the core matched up with the refractive index of the cladding to create total internal reflection. And the light can continue its journey having been totally internally reflected. In order for total internal reflection to happen, the light needs to be inside a material with a high refractive index compared to the material on the outside. Just like in the simulation where we had glass moving towards air, that created total internal reflection. So the cladding needs to have an index of refraction that's smaller than that of the core. There are many different problems with fibre optics. We're going to discuss a few of those now. The first one is modal dispersion. And modal refers to the different physical paths that are taken through the material. So for example, the light might travel straight through, it might have to bounce around quite a lot, or it might do something in between. And what this means is that the different paths of light are arriving at different times because they're traveling different distances. So if you are sending out a signal that's composed of pulses, then what you're getting at the other end are the pulses that are arriving at first. They're arriving the quickest because they're traveling straight through. And then just after that, you're getting those that are traveling a slightly longer route and are delayed slightly. And then finally, you're getting those pulses that are traveling the longest distance and are arriving last. And this concept is called pulse broadening. And that's because we started off with quite narrow pulses, and now all of a sudden they're much wider, caused by the delay in arrival times. So modal dispersion leads to pulse broadening. Another problem that we see is called material dispersion. And this can also lead to pulse broadening. So material dispersion works the same way as modal dispersion, except for the fact that we're talking about colour. And when we have a material with an index of refraction, that index of refraction will slow down different wavelengths by different amounts. We all know that a glass prism will refract red light differently than it refracts blue light, not by a huge amount, but enough to split white light into its component parts. So if you are sending light with multiple different wavelengths through, then what's going to happen is that the red light is going to be arriving at a different time compared with green light and with purple light. So depending upon the wavelength, you're going to be getting different arrival times of the different colours, and that can also lead to pulse broadening. The last problem that we're going to be talking about is absorption. And this refers to the fact that the core, which is made of glass or plastic, is not 100% transparent. It is absorbing some of the energy from that pulse. So if you are sending out pulses, after several kilometers of fibre optics, some of that light will have been absorbed, so your pulse is going to look something more along the lines of this. So it's going to be attenuated. The intensity of that light, the amplitude, the brightness of that light is going to be reduced. And the way that we solve these problems is by having something called repeater stations. So we have a transmitter emitting the light down a long section of fibre optics, and then we have a repeater station. And that repeater station analyzes the signal that it's receiving and regenerates it, and then sends that signal out again, ready to be received at the other end by the receiving electronics.